Let's get this started. Okay, so reading goods are on your desk, yeah? Because I'm going to come check those. We probably looked through the chapter and tried to find binary acid and ternary acid, but a lot of that was probably from your memory. So, what does it mean to be a binary acid, Lewis? Two elements, and that's it. Just two elements. So, of all of these acids up here, which ones are the binary acids? H2S, what else? Uh-huh.
HI,
Just these four. Okay. When you're naming a binary acid, what do you say to tell me it's binary? Hydro. Okay? If you say hydro, does that mean it's an acid? No. If I say hydro, it means it's binary. If I say acid, that means it's an acid. Okay? So, like, for example, hydrochloric acid means it's an acid. Okay? Hydro just means it's a binary acid with two different elements. So, name this one. We just named this one, actually. Hydrochloric acid. Good. This one. Hydroiodic acid. This one. Hydrobromic acid. So there's really no variation of the ending, right? It's just always ic acid, ic acid, ic acid, ic acid. Name that first one. Hydrosulfuric acid, okay? So the binary ones should be fairly easy. The ones that are ternary are going to be the ones with more than two different types of elements, and their endings are different. So how do you change the ending of a polyatomic? So for example, name this polyatomic here. So name the polyatomic first. Sulfate goes to what? Ic. Remember the ic, I ate too much, yeah, the cheesy things right there. Sulfate goes to sulfuric, actually, and the name of the acid is? Hold on, just what was that first thing we said? Okay, just straight sulfuric, okay. Sulfuric acid. No hydro, because it's not binary. Tell me another polyatomic that's the 8 version that's up here, right here. Where's chlorate? HCl3. This is the chlorate. So name that acid.
Chloric acid.
Chlorate goes to chloric acid. Good. Name that polyatomic ion. Hold on, the polyatomic is what? Chlorite, and the acid is? Chlorous acid, right. Because that's the tendinitis, right? The ite and those go together. So that's chlorite, and chlorite goes to chlorose acid. Okay, then we have an upper and lower variation of chlorate. What was the lower one? After we went from chlorite, we went to hypochlorite, right? So like my great example of a hypodermic needle, yeah? Under the skin, okay. So we went down 1 O. So that's not changing it too much. It's just we have a prefix now. Hypochlorous acid. How do we change this one when we went up? I know you want to say hyper, but let's just go per. Yeah. Perchlorous or chloric acid. Perchloric acid. Okay, so that's how we vary the names, right? Let's go one more. Let's name one of these. Let's name the lower one. What's that polyatomic? I think I heard it. There's no chrome in there, right? Is that chromium?
No, that's carbon.
That's carbon.
Carbonate.
Oxalate. Good, oxalate. So how does oxalate get changed? Oxalic acid, right. Oxalic or oxalic acid. That's the weird one. Okay. Now, these are obviously not acids. What are they? Bases. Anything with a hydroxide is going to be a base. Anything with an H plus in the front is going to be an acid. Let's do aluminum hydroxide. Tell me your process of writing the formula. Parentheses. Where's the 3 coming from? Charge of aluminum, right. OH is charge? Negative 1 crosses down to get like an invisible 1, right? So this is a little bit of nomenclature review because you'll be using this a lot as we go through finding our acids, finding our bases, writing out chemical reactions, reading them. So I want you to be really comfortable with this. But I want to see how well you did on your reading guide. I've got to activate that. Where's the marker? There's a marker hiding someplace. I don't know where it is. I'll find it. Let me go ahead and turn on the Socrative. The Socrative. Ready, set? It's all you. Here, huh? It's open reading guide, of course, okay? That's why your reading guide's on your desk. I'm going to check your reading guide super duper fast. So I'm just going to kind of just like ninja. Short line, so I'm in 2 minutes we should be done. Okay, if you did a fantastic job, a very detailed job on your reading guide, your notes can be kind of added to your reading guide if you want to. You'll find some stuff that's really similar. The reading guide is supposed to serve as a really good introduction to stuff, so I can kind of expand and can make the connections and show you how things are related to each other, and we can kind of get more into the details. A lot of this stuff I think is a kind of common knowledge, except for the more definition, application-based stuff with acids and bases. So this beginning stuff I'm going to kind of run through, because we've all, maybe we all are not as bad as I was as a child, we've all tasted soap. Like maybe mom put a bar of soap in your mouth because you said a bad word. Yeah? Like the bar gets stuck in your teeth and everything. Yeah, it's like with you for days. It's real bad. Okay, maybe that's just me. I see a couple people are like, yeah, I know what you're talking about. Okay, so we all know bases are bitter. Okay, that's like soap. Soap is bitter. I'm gonna start with bases actually on this side. We all probably have washed our hands. Yeah, once or twice. Yeah, maybe. But that soap is slippery. Bases are slippery. Yeah.
Isn't like bleach and acid?
Hypochlorous acid and sodium hypochlorite, or no, sodium hypochlorite and something else is in bleach. I can't remember because it's a chlorine-based bleach and something else, but they have both things in it because they're good cleaning agents. A lot of cleaning agents are soapy.
They're slippery.
Yeah, that's actually a sodium hypochlorite, which is a salt, but it's a basic salt. So we'll talk about that on Friday. All right, so these are two common characteristics you'll know a lot about, right? Going to the acid side on characteristics. We've all probably had lemon juice or orange juice or some sort of citrus fruit, and that's sour. That's something we're all really familiar with. We've all probably had some sort of like a paper cut or something on our hands, and then I don't know if you've ever cut lemons, that burns when it gets on your cut. So there's two ways that acids burn though. It's like a tingling sensation when it burns your hands, or there's like literally an acid burn where you're scarred for life. There's a scar because a piece of your skin has been, corroded to the point where it's no longer there. So there's two types of burns, but a lot of times we'll associate burning sensations with acids and like bitterness and slipperiness to bases, but bases can actually chemically burn you. They don't burn you like, oh, this cut is burning. Okay, they can chemically burn you as well. So there's really strong acids and there are really strong bases, and they can both harm you in terms of burning. For example, we used lye to make soap in AP Chemistry last year, and I told them to have their goggles on and gloves on at all times because it's extremely corrosive. And one of my girls picked her goggles up and then put them back down. She got about 12 hours later a burn on her face where she touched her face with a strong base, and she had like a little Tupac scar or something like that. I don't know what you call it, but she had a scar there and she burned herself. Yeah.
Is that stuff safe for you to get out of students on last year? What is it?
It's neutralized over. It takes a while to neutralize. That's why it's like do not use until July or whatever. Yeah, it's safe. Okay, so to the top there, you probably noticed acids have an H plus associated with them, bases have an OH minus associated with them. So our acids have the cation, and the bases have the anion that are the most important part of that specific compound. So a lot of this is not new. The reactivity part's not really new either, but I'll go ahead and highlight this, and then the conductivity. So the reactivity, we've dealt with this before. What kind of reaction is this? What type of our 5 types, huh? Single displacement or single replacement reaction. The metal is replacing the H out of the acid, so they change places. So the H plus is replaced, and as it's replaced, it makes H2 gas. So that's a common indication of an acid reacting with a metal. We've done that in the lab before. Bases are different when they react with metals. They just don't, okay? So this one's easy to see that it can react because metal is a cation. Metals commonly form cations anyway. Cation replaces cation. That's why that works. That's why that can be replaced. Bases, the basic part of a base is not the cation. It's the anion, right? So this metal, which is a cation, trying to replace this cation, it can happen, but it stays there for a nanosecond and then it reverts right back to the original form, basically looking like to us nothing happened. So we just generally call that a no reaction because it's reversible and it goes right back to the original form. So we'll see some no reactions happening in the lab like we did in one of our replacement reactions labs. Good so far? Thanks. Like 3 people should go. Thanks. Okay. Thanks. The last pieces here are referring back to some information we talked about last unit. So we're going to kind of, oh, and by the way, y'all's multiple choice was pretty dang good. I've had a lot of people in the 80s and 90s on multiple choice. 93s, 95, stuff like that. So there may have been like 2 questions you missed. And I had some people lower than that, but generally I was very happy with multiple choice. I'm still scoring this for your okay, so on these, this is relating back to our conductivity of property with ions that are being created. Well, what's happening here is we're really focusing on how this acid is interacting with water. So when that reacts with or interacts with water, water is doing what with the H from the acid? It's what? So what's another word for taking? Like, I accept your offer, accepting, yeah, accepting, okay. So this H plus is being donated from the acid, it's being accepted by the water. Those are words we're going to use a lot today. So you can see that transfer process, right? You can see the results of it too. What is this called? Hydronium. Who knew that on the quiz? Yay, it's on the board. It's the word of the day as well. Just trying to help a brother out. Okay, so this is hydronium. Hydronium is a very common ion that's coming from acids. Electrolytes just mean basically you're going to be able to conduct electricity. We're all good with that. And then this is just a reminder again of how our bonds form in water. They're polar covalent bonds. Okay, so that's ionization of acids. Ionization of bases, they don't technically have to interact with water. The ionization of a base just takes place in water. But you'll notice water is not involved in this chemical reaction, so it's in water, but it's not interacting with water. Does that difference kind of shine through here? That's interacting with water because it needs water to take the H+. This is like, hey, I just need to be sitting in water, and then it splits in half. Okay, these are going to also be electrolytes. This being a strong acid and this being a strong base, they make a lot of ions. They're really, really, really strong electrolytes. And then you'll see there's 2 different words up here, dissociate and ionize, and I'm going to be using them both today. Ionization, I'm going to kind of specifically keep with the acid category, and dissociation, I'm going to kind of keep with the basic category. But we can interchange them. They're essentially, for us, the same thing. Okay, let's go on to business. Oh, I'm going to skip that, because I had some people tell me the foldable is not as helpful. So I have an option to make notes via foldable or notes via just general paper. So it's on you on how you want to do this, but I do have paper if you want any paper. So, before I go into this, on your reading guide, what did Arrhenius specify acids and bases were interacting with? Huh? Water. Okay, he said they take place in what solution? Aqueous solution. Okay, so when I was your age, I was like, oh my gosh, I cannot remember these definitions for anything. So I made up my little cheesy Arrhenius aqueous jingle. I'm not going to do it for you, okay? But Arrhenius aqueous, Arrhenius aqueous, Arrhenius aqueous. If you remember, Arrhenius definitions are related to how they interact or behave in aqueous solution. You can always get these right, okay? We literally just write this down. Do you notice? We're talking about how it interacts with water. We just have that in the bottom of the table. Yeah? Okay, so write down what you want to, but I'm not going to spend a whole lot of time here. We're basically just trying to figure out how does this stuff interact with water or aqueous solution. So hydronium's being made in aqueous solution is indicative of an acid, an Arrhenius acid. And hydroxides being formed in aqueous solution is indicative of a basic compound, or an Arrhenius base. So Arrhenius was the first guy to kind of go, hey, I think there's 2 different compounds. I think they act differently in water. I'm going to say that all acids are always going to make hydronium, and all bases are always going to make hydroxide. But you know, always, it's kind of a funky word. Does something always happen? Are there exceptions to rules? Yes, okay. Arrhenius was very narrow-minded. He was like, this is always going to happen. Anytime there's hydronium, it means there's an acid. All acids, every single one of them, and all bases are going to make these things happen. But he was narrow-minded. So 2 guys came afterwards, and they're like, Arrhenius, we think you should expand your definition to being more inclusive of everything that's out in the world. Who are those 2 guys who came after Arrhenius? Bronsted and Lowry, right. Bronsted-Lowry acids and Bronsted-Lowry bases was then coined as extended definitions of acids and bases. They're extending from Arrhenius. So Arrhenius kind of started this whole definition process, and Bronsted and Lowry came in, and they were like, no, there's a bit more to it. They said acids and bases are basically more about how protons are exchanged. Proton. See I have here? Proton, hydrogen ion. We have talked about this a long time ago. Why is it okay for me to call a hydrogen ion a proton? So what happened? What was it before it was just a proton? What was the hydrogen ion, a hydrogen atom consisting of? One proton and one electron. That's all it is. There's no neutron in it. How do I know there's no neutron? It's got a mass of 1. Well, who's making up the mass? The proton. The electron is essentially negligible in mass. So the proton is making up the only mass, atomic mass unit of 1. So what's happened? What has happened when I've come to the ion form? How did it become an ion? Right. It lost the electron, meaning the only thing left is the proton. So that's why it's okay for us to call H plus a proton. Okay, so this is just an extended version of Arrhenius. So not only are we saying, yeah, the things that make hydroniums and things that make hydroxides are acids and bases respectively, anything that's a proton donor is an acid, and anything that's a proton acceptor is a base. Now, that's simply memorization. Or you can go with my way. When I was, 15, 16, whatever you guys are, I was like, oh, okay, all Bronsted acids, they're bad acids. Okay, they're all bad acids. Why are they bad acids? They're Bronsted acid donors. So bad means Bronsted acid donors. Got it? They're bad acids. You gotta be careful with. And then these are, there's nothing good about them. Blah. Bronsted bases are acceptors. Blah. Blah, blah, blah. There you go. Bad acids are acids. Our Bronsted acids are donors. And blah is Bronsted bases are acceptors. Acceptors of what? Protons. And donors of what? Protons, meaning H pluses. Another way to say that is hydronia. So if I say any of these words, I actually mean the same thing. Proton is the same as H plus, which is the same as hydronium, because hydronium is just like an H plus attached to a water. These are all essentially the same for us, okay? Thumbs up, we got Arrhenius and Bronsted Lowry. Okay, so the next guy was like, you guys are being so discriminatory. You're just talking about protons and just talking about how things interact with water. What about the electrons, right? What about talking about how electrons are exchanged, or electrons are shared? Who's our next guy? Lewis. Lewis. Where have we seen that before? Lewis dot structures. What were those dots representing? Yes. They were representing electrons. And so he was like, guys, what about the electrons? How do they come into play? And we said, okay, we can talk about electrons. We can talk about how the acids and bases are going to be sharing their electrons or being shared with. This one we will see probably least often out of all of them, but we need to know the definition. So this one's not focusing on protons, it's focusing on electrons. Pairs of electrons, okay? Acids are acceptors in this one. Acid acceptors. Sorry, I know the other one was an acceptor in the Bronsted Lowry. But we're talking about a totally different subatomic particle, so they have to be opposites. They have to be different. So Lewis electron pairs are kind of the highlight of his definition. So now these definitions should kind of mean something more to you than just like what you're like proton doing or whatever that means, but something right down on paper. Okay? And I'll show you how these interact. I have some pictures and I have some actual chemical formulas for you. So if you're a Lewis acid, you're accepting lone pairs, and if you're a Lewis base, you have a lone pair. You have it and you're going to share it. Okay. So So let's look at our pictures, and you tell me what is being represented in terms of definitions. So look at these two guys playing ball, aka protons. Say again. Bronsted-Lowry definition. It's like, here, have a proton. Gee, thanks. Okay. Exchange of protons is Bronsted-Lowry definition. That one. Why? Arrhenius. True, but it's interacting with water. Okay, Arrhenius aqueous, right? Interacting with water. So you can see interacting with water. This one actually has both definitions of two different people involved, okay? The mere fact that it's got water involved is Arrhenius, right? But what's happening to this strong acid? What is it doing? Donating a what? A proton, right? See this proton here? It's going, hey, water, you can have it. How do you know that? Because what happened to water? It turned into hydronium by gaining a proton, right? So not only are we representing Arrhenius acid here, we're also representing a Bronsted-Lowry acid, or a bad acid, whatever you call it. We can do that. So we can see both definitions involved. Okay? The last one here, what are we focusing on? Lewis, how do you know? Okay? Which of these, if this has the lone pair, and it's donating it here, and this one's accepting it, which is the Lewis acid? The left one. Good, the boron trifluoride. So this is the Lewis acid because it's the acceptor in this case. And this is the Lewis base because it's the donor. That's the one that's opposite. Okay? Yay! Definitions down. Yeah.
Wait, so where's the hydrogen involved?
This one is not focused on hydrogen ion chemistry. It's more about the electrons.
So it's still considered an acid even though it doesn't have hydrogen?
Right. So that's what it's saying. You know, just knowing there's a hydrogen involved in an acid is not enough. We have to know how it interacts with water, it makes hydronium, the fact that it's got a proton donor in the Bronsted-Lowry, and the fact that it's in a lone pair acceptor in Lewis. It's a bit more expansive. Yeah.
So all these guys have the idea?
Yeah, they're all definitions of acids and all definitions of bases. They're just kind of in different perspectives. They're all correct. At least I think so. Okay. Now let's get to the question on your reading guide that was concerned about strength. Okay, we know we all have to strong. We all know concentrated, you know, oh, that tea is really strong, that Kool-Aid's really strong, it's really concentrated. But the word strong for us in acid-base chemistry means something totally different. So I'm actually going to start here with the blue definition, okay? Strong does not mean concentrated. Strong means 100% ionization or dissociation, okay? So this is the important part there. Did you write that on your reading guide? Did you know what it meant? No? Okay, I got you. What does this mean? It means, we'll do HCl. When HCl ionizes, I'm going to kind of just take water out of the situation for a minute. When it ionizes, it makes H plus and Cl minus. That's what it does. And when it ionizes 100%, 100% of this goes away to become this. So there's 100% products formed. How many reactants are left? None. 0% of this is left. So does HCl itself truly exist? It's questionable, right? Mainly, if I have in my stock solutions in the back, my stock solutions of HCl, I could probably go, if I was, on the Magic School Bus, zoom down in there, nanoscale, I probably would find very few of those. I would find a lot of these and these, because most of the stuff is ionizing. The reason it's a strong acid is because the only acidic part of this, that itself is not really the acid. That's not the part that's causing the pH to drop, all the way down to 0. It's this. This is the true acid. That's the thing that's causing the pH to drop. So if I set that free, the pH is going to plummet. It's down closer to 0. So that's really what the acidic portion of it is. And on a base, what's the basic portion? The hydroxide, okay? So really focusing on more of the details that are inside of the atoms. Okay, so there's only 6 strong acids in the world. There's only 6 of them that 100% ionize. They are as follows. You must know these. Give me the formulas. Okay, and how does it ionize? And see that single arrow here? This single forward arrow, it's telling me 100% ionization. If you wrote 2 arrows, a back and forth arrow, a reversible arrow, it would mean something different. We're going to talk about that in a little bit. Next one, HI. 100% ionizes 2. And I minus. Next, HBr. Hydrobromic acid ionizes 2. If you just want to write the the formulas, I know you guys know these. We just went over a lot of these, so you don't write like everything down. Nitric acid, HNO3. How do you know that? What's the good? So nitric came from nitrate, and nitrate is NO3 1 minus. NH is always an H plus. It's always got a plus 1 charge. How does that ionize? Yeah, just the stuff that made it. Don't be a homewrecker. Keep the nitrate as a happy family. Just take the ions apart. Don't like particulate every single thing. All right. Perchloric acid came from HClO4. Okay. And it makes perchlorate, ClO4 1 minus. Last one, H2SO4. Where did the 2 come from? The charge of sulfates SO4 2 minus, you crisscross it down, so that's where you get your 2 from. How does that ionize? Good. There's 2 of these H's, and you have to represent that with a coefficient of 2 as you ionize. And what's the last bit? Okay. Which of these are monoprotic acids? Monoprotic acids. What's mono mean? One. What does protic refer to? Proton. Which of these has 1 proton? The first 5. These are all monoprotic acids. The last one is a diprotic acid because there's 2 protons. Diprotic acid. Okay, triprotic acid, example. It's not a strong acid, but it's a triprotic acid. Oh, hydronium maybe, but I'm going to stick with hydronium as its own special thing. Phosphoric acid, okay. So phosphoric acid would be a triprotic acid, but is it on our list of 6? No. So if it's not a strong acid, guess what? It's a weak acid. So acetic acid, nitrous acid, hydrofluoric acid, chloric acid, hypochlorous acid, anything like that, that's all going to be weak because it's not one of the 6 strong. So pretty much if you know you're 6 strong, then everything else is weak. It's easy to figure out which ones are weak. So, like I said here, what's the name of this one? That one? Acetic acid. Is it strong or weak? Weak. Okay. Though it's weak acid, we can still say it is, what would this kind of tell us? Concentrated weak acid. That you can describe it in 2 ways. You can describe the concentration of it, and you can describe the strength of it in 2 different ways. Okay, so it's a concentrated weak acid. Describe this one. Dilute strong acid. Okay? You'll see some of that when your problem sets. All right, ready to go? Let's go to bases. We have to show the love to both sides. Yeah, let's go bases here. Okay, so bases have hydroxides. They 100% ionize just the same way. They will have 0% at the end. They'll have 0% reactants left, and at the end, 100%, not 1,000%, 100% products. Sorry, today's a note-heavy day. First day of meeting, it always is. My bad. It happens. And then I'll tell you what this blank is in a second. I'm going to go through the strong bases first. There are 8 strong bases. They are in group 1A and 2A. What is the first metal in group 1A? Lithium. First one. So group 1A, you're skipping hydrogen because it's a non-metal, right? So you go lithium, what's next?
Sodium.
Sodium, next. Potassium, next. Rubidium and cesium, cesium, whatever you'll say is good. There, stop there, okay? These are all in group 1A. What's next to cesium or cesium in group 2A? Barium. Next on top, strontium and calcium. Stop there. Those are the 8 strong bases in group 1A and 2A. Not all of group 2A is considered strong. But my easy way to remember these 8 strong bases is they form a lowercase b. See? You know like a lowercase b? Yeah, like that. See? B. I'm trying to draw b. It's hard. It's lowercase b in the base for the group 1A and 2A. Just trying to help where they're at. Okay. Now, these have to be with a hydroxide, right? So, all of the group 1As are going to be like lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, okay? So, they're all with a charge of 1, so they get crisscrossed down as a 1, right? How are the other 3 different? Right, so tell me the formula. Uh-huh. So you like my parentheses with the 2 on the outside? Yeah, me too. Make sure the 2's on the outside, not the inside. And make sure there's parentheses. Let's start with parentheses, and then put the 2 on the outside. Some of us put, like, this. Where does that 2 go? Who's it applying to? Just hydrogen. Nay. That would be stupid. Don't do it. Too much work. Too much work. Okay, so these are how you would write your bases. Okay. Next on the chopping block is pH. Oh, no, we gotta do conjugates first. Okay, conjugates and then pH. Okay, I'm skipping the weak stuff for just a moment. I'm gonna come back to it tomorrow. And that. That's just pictures. Ooh, ah, look. It's 100% ionized. What? It's strong. Guess what weak stuff does? Doesn't do that. Here it is attached to each other. Oh my gosh, they're still attached. They're still attached. They ionized. Okay, look. One of them ionized. Okay, and there's more pictures. I'll go through pictures tomorrow. I'm going for definitions today. Okay, conjugates. That has that paper sheet. Yeah, there's like papers like this. Everybody get one? Missing. Oh. Extras. You guys need one? Okay, there's extras. I'll get them later. All right, do not write down all of these definitions, okay? I'm going to give you an example, because you already wrote down definitions in the reading guide, so I'm going to give you an example to kind of go with these, because the examples mean more than this nonsense here, okay? This is for you if you need it. First of all, conjugates, the most important thing you probably do want to write is conjugates are going to be considered a product, not a reactant, okay? So when you have a balanced chemical equation, you have your reactants, when we will call those acids and bases, and you'll have your products, and we'll call those conjugate acids and conjugate bases. So we should add the word conjugate, because it's like a set of 2 reactants. So I'm going to give you an example of ammonia. We all know NH3 is ammonia? Better now, okay? Make sure you know that. It's ammonia. Ammonia reacts with water. Ammonia, is that an acid or a base? Do we know that? It's basic, right? If I'm a Bronsted-Lowry base, what do I do? That's a bad acid. You accept what? From, in this case, water. Okay, so water, you know, is HOH, yeah? HOH is H2O. Give the H plus to ammonia and make what? What's the name of that? Ammonium. Okay, ammonia, ammonium. And what's left of for water? Huh? OH. Minus? Yeah. Hydroxide? Okay, so ammonia accepted the H plus, made itself to be ammonium, and left hydroxide, all that fun stuff, okay? So if you just told me ammonia accepted, you told me was that acid or base? Base. What became of ammonia is now ammonium, yeah? Conjugate acids come from bases. So this base here made its own conjugate acid. So it's a pairing. This and this, they complete each other. It's a base, and the base makes a conjugate acid. And I'm going to tell you kind of the reasoning why. Sometimes I don't, but I will here. If I reverse this reaction, if I went from here to here, what is this ammonium going to do? You can see that it did what from here to here. We're not talking about electrons here. It lost a proton, yeah? Okay, so it donated a proton? Is that what you're actually saying? Didn't this donate a proton back to hydroxide? Yeah, so it's a bad acid. It's a donor. It's an acid. That's why it's the conjugate acid here in the reverse direction. So that's why it's okay to call that the conjugate acid and not that. Because that doesn't even have an extra H to give away. It's stuck. It needs that. Because you can see it went back to water in the reverse direction. But once you figure out who's the base, it's easy to figure out who the conjugate acid is of itself. So if that's the base, this has to be the acid, just the general acid, right? So that base and acid react. This acid, guess what it makes? A conjugate base. Thank you. This acid donated, and as it kind of transformed, it turned to hydroxide, and it's now considered the conjugate base. So they're always in pairs. And so basically you can read this now, and it should make sense. The species formed once the base accepts the hydrogen. So that's the species formed once the base accepted the hydrogen. And there's an example here. Let's look at the acid definition too, or the conjugate base definition too. So conjugate bases come from acids. I'll show you another example in just a second on your sheet. The wordings of it kind of weird, but the examples actually are much more helpful. We're going to do those now. If you really want to copy not every bit of this, you can do that from online. So conjugate bases come from acids. Conjugates are always in the products. That's kind of our main two things we're focusing on. Let's do the first example on the notes that I gave out. Let's do a couple of these together, and I think this will make more sense. But you'll notice the Bronsted acid and Bronsted Lowry acid and Bronsted Lowry base are the two things that we're really honing in on here, okay? So here's where we are. Do you see on your paper where we are? Yeah? Okay. So your job is to first kind of assess the situation. Let's assess this. What's happening to acetic acid from reactants to products? It what? So there's another word for that? Donated a proton, right? It donated its proton to water. So what is this? An acid, a bad acid, right? Bronsted acid donor is an acid. So if that's the acid, where is its conjugate base? Yes, whatever it became. The conjugate base comes from its acid. Okay, so then what do we label water as? The base, because you can't be an acid and acid. Acids and acids don't react. That's the base because it's accepted, and this would be its conjugate acid. It's the opposite. The examples make things kind of a bit more clear. Let's do the second one. Assess the situation here. What did this do? It, use your words, donated an H plus to sulfite. Yeah, it's a donor, so it's a an acid, and the acid always makes whatever it became. So the HCl became a Cl minus, and it's a what? Conjugate base, right? You make the opposite. And sulfite in this case would be the base because it accepted, right? Bronsted bases are acceptors. Accepted, and this, its partner in crime here is the conjugate acid. Let's do 2 more. What is this one doing? Look and see the pairings here. What did ammonia, what did it become? Ammonium. How did it get from here to here? It accepted this guy's H+. So you're an acceptor. Base. You're the acceptor, you're the base. Your friend over here? No, this one right here.
C is
Conjugate acid, good. So you hear nitrous acid is the acid and its friend, conjugate base. Thumbs up if you get how this is going here. All right, you do the next 3. We'll check them. Do the next 3. Keys, Sam, Benny. In order. After this, we'll take a quick break. I know today's a talkie, Mr. Monday. So, take a break. We'll go see a friend. Maybe we can do some, like, proton exchange. Yeah? Unless you're going to do electron exchange. I mean, I'm cool with that.
They smell weird.
You can do it. Alright, check yourself before you wreck yourself, people. Make sure you're checking. CQ.
You get the acid.
You're seated. Okay, thumbs up. You see how to do conjugates? Okay, they're all based on the Lowry, the Bronsted-Lowry definition about proton exchange. Last thing I want to do together, and then we'll take our break actually. Write the formula for ammonia acting as an Arrhenius base. So if I say that, what is Arrhenius kind of saying to you? In water, okay, in aqueous solution. So how is this reaction happening? I thought you said ammonium instead of hydronium, but you meant ammonium, right? Okay, and hydroxide. Because if it's acting as an Arrhenius base means, one, it has to be in water, and what do all Arrhenius bases make in water? Hydroxide. So these 2 things here are required to make it act as an Arrhenius base. Definitions, I know they're kind of out there sometimes, but you have to apply them. All right, so get up, walk around for 2 minutes, come back to me. We got to do pH after this. Okay, so go see a friend, some water, be back. I'm starting without you. Come see the water balls. Go quickly. Run like the wind. I'm sorry. I have paper towels. That's it. Oh, no. I have tissues here. I don't know how soft they are.
Your teacher ones?
My teacher ones. Andale, andale. I also have other teacher tissues. And you'll be done in 30 minutes. Because I'm gonna start to get comfortable and get all your stuff prepped and come and do it because I've got so we're coming. I can't help everybody, so it's gonna take time. I've got a lot of people coming this weekend.
What's your project?
Okay, come back to me in 10 seconds. Oh, wait, marker? They're water polymers. Yeah.
Can I juggle these?
No?
Alright.
Are these like the smaller marbles? Where do you
Okay,
get them?
I'm gonna restart class back. So let's do this. Let's do this later. Okay. Back to me. Back to me. Let me see your pretty faces. Okay. So this is the last thing we'll do today. We'll do pH. Talk about pH. Apply some logs. Who knows what logs are? Logs as in algebra 2? Logarithms? Yeah, logarithms. Okay. I hope everybody. Right. Shh. Okay. So, we've all heard of pH scale. What does it range from? 0 to 14 is what most people would say. 0 to 14. But 0 to 14 is a little bit of a lie. There are such things as superacids and superbases. And 0 to 14 is our general scale from here to here, right? There are such things that will have superacids that are in the negative pHs, and then we'll have things that are like, 15, 16. They're superbases. Yeah, Nicki Minaj. So we'll go with general 0 to 14, but we will see some negatives. Don't be scared. If you see above 14, don't be scared. It's okay. Well, those are just above and beyond, right? What's our neutral point? 7. Okay. So we've been talking this whole time about H pluses and OH minuses. At 7, our H plus concentration bracket means concentration. Bracket means molarity. You need to know that. Write that down for yourself someplace. Bracket means molarity. So the H plus concentration equals the hydroxide concentration. And I'm lazy. I will always write H plus. I don't like to write hydronium. But most of my examples will have hydronium in them. Hydronium and hydronium and H plus are the same thing. Okay? So that's the point at which they're equal. So you tell me, what's greater at the acidic side? Hydronium or hydroxide? If it's an acid. Which one do you associate? Thank you. So you're saying hydronium is greater than hydroxide on the acidic side of the pH scale. And on the basic side, what would you say?
Hydroxide.
Okay. Hydroxide is greater. than hydronium. Okay, the middle point is when hydronium and hydroxide are equal, and both of those are equal to 1 times 10 to the negative 7th molar. 1 times 10 to the negative 7th molar. You need to know this information. I'm just not writing it down just for me. It's for you too. So on this one, hydronium, give me a number that it could be. 1 times 10 to the... It's got to be still negative, okay? If hydronium is greater, it's going to be greater than 1 times 10 to the negative 7th, yeah? Because the middle point is where they're equal. So give me a number that's greater than 1 times 10 to the negative 7th. Negative 6, okay, or negative 5th, negative 4th, negative 3rd. Anything a larger magnitude, which is a smaller negative number. Okay, so this could be like 10 to the negative 5th. That might be 1 times 10 to the negative 8th, 9th. Okay, so that's a smaller number, so it's more negative decimal, or exponent. So over here, what would hydronium be? If hydronium is less than hydroxide, what could hydronium be? So 1 times 10 to the negative 9th, negative 10th, right? And this would be like 1 times 10 to the negative 4th, which is a bigger number. So you'll see some qualitative comparisons with these hydroxides and hydroniums. Okay, and I know you're all wondering, like, why does pH matter? First of all, from biology, where did pH come up? Lakes, pH of lakes for organisms. For organisms. What else? What else?
Rivers.
Hold on. I'm waiting for Maggie and Strata to tell me. When is pH important? This might be related to your Mythbusters experiment.
Hydrogen bonds.
Acid-base reaction.
There are experiments on protein denaturation. Okay, so denaturing proteins and enzymes. Okay, yeah, okay.
I was still laughing at things.
Lakes.
Lame.
Okay. Back in the day, with me. Back in the day, this was important because a specific Danish beer company was killing some of their customers by accident, making their beverages too acidic. So then this nice guy, his name is unfortunate, Soren Sorensen. He said, we gotta mess with this recipe. Apparently there's something wrong. We need to come up with a way to test our product before we put it on the, out to the customers. So he came up with the pH scale to say, okay, the happy region is here. This is bad. This is death. This is good. Okay. So he wanted to make sure that their customers survived. If not, they're out of business, right? So it was all from the business perspective. So I thought that was kind of cool to include. But with me, pH. Does anybody know what the P stands for in pH? Never mind. I always try these things and no one knows. Power of hydrogen. Okay, it's the power of the hydrogen. If your pH is really, really blank, it's really acidic. Low. If you have a really low pH, that means you have actually a higher power of hydrogen, which is a higher H plus concentration. So low pH is a high H plus concentration. So a high pH is a low pH concentration. They're inversely related, yeah? Okay, so if they're inversely related, that means that when we calculate these things, inverse usually means there's a negative involved someplace. We'll see that in our calculation shortly. I have a video for you. I'll show you in a little bit. Write down this auto-ionization of water. There's a 2 there. Water plays with other waters, and they what's auto mean? Self-ionize each other. So we have in a water, making hydronium and hydroxide. Which of these is the acid? Either one. So this one's an acid, so what's it doing? Donating, thank you. It's a donor. It's donating an H here to make hydronium, leaving that water to be hydroxide. So this water is acting as the base. So what am I telling you water can do? It can act as either acid or base. What do you call somebody who can write with their left hand and their right hand? Okay, so what do you call water? Ampho. Amphoteric. I'm still spelling it wrong. I'm so sorry. I forgot my H. Amphoteric is supposed to kind of sound like, you know, ambidextrous. I can never say that. But this is supposed to kind of resemble a proton. Amphoteric, proton. It can do both. Okay. Amphoteric means you can act as an acid or a base. Okay. That's just a word you should know. Okay, so let's get into pH calculation. So, calculators out probably. You'll, unless you can do logs in your head. Logs in your head?
I can do it.
Me too. Okay. Just look at it. Okay. This does not mean turn around and talk to people. We want to get through so you can practice in class. My goal every day. Sit with, use a straw right now because mine, these have, oh, they do have logs. I'll give it in a second. Give it a second. Okay. These formulas, are they on your reading guide?
Yes.
All of these on your reading guide?
No.
Yeah?
Not a whole.
If they're all in your reading guide, then don't write them down again. If you,
Only one.
okay, you probably want to know all of these. Okay? We are going to work with these, and you all probably accidentally memorize them by tonight. Okay? If not, you already need to work on them. Okay? We will be using these a lot. You should not have to go, oh, wait one second, Miss Hill, let me flip back. 5 minutes later, we finally have the equation. Okay, that's like knowing the polyatomic ions. It's more of a expedited process to help with you in your processing than, you know, simply we need to memorize, but we will be using these a lot. So we talked about the inverse relationship. Now you can see why. And this, a lot of these over here deal with pH, and a lot of these over here deal with pOH, but they can be used interchangeably. You can use them for lots of different reasons. So I'm just going to kind of point out some tips here. You can write, listen, whatever you need to do. But your pH, your power of hydrogen, is only referring to your hydronium or H plus concentration. So as pH, as hydronium goes up, what do we say happened to pH? It went down, and that's simply because there's a negative right here. That negative, that's the inverse relationship. Over here we have pOH, so it's referring to the OH concentration. If I bring the hydroxide concentration down, what do you think happens to the pOH? It's going to go up. Okay, they're inversely related because of the negative log here. Then we have, how do you relate pH and pOH? Most of us are more comfortable with talking about pH. You're like, low pH is acidic, high pH is basic. It's hard to talk about pOH because you're just less experienced with that, but you can still relate them. They always add up to 14. Where has 14 come into play before? The theoretical max of the pH scale, right? You'll see 14 pop up a lot. For example, over here. So pH plus pOH is 14. Hydroxide concentration times hydronium concentration is 1 times 10 to the negative 14. At neutral, what was the concentration I told you? 1 times 10 to the negative 7. So how does this work mathematically? I'm going to kind of draw an arrow here. 1 times 10 to the negative 7 molar. That's the hydroxide. And then 1 times 10 to the negative 7th molar for hydronium. How does that equal 14? Exponents add when you're multiplying. Exponents do what when you're dividing? Subtract. We'll be using that throughout, okay? Finish writing those down and some of that. Finish writing some of this. Sorry. Okay, great. I'll send it over in class. Okay, so we're going to be using these pH formulas, but I'm not going to just straight out go, here, Sarah, the hydronium concentration is this, here, take it and go. Sometimes I'm going to say the acid's concentration or the base's concentration is blank, and you interpret what that means. So it's a little extension. So I might say, oh, I'm going to give you 2 molar hydrochloric acid. Your thought process should be, oh, is hydrochloric acid a strong acid? Yes. And then you go, oh, I know what that means. That means hydrochloric acid makes 100% H plus and Cl minus. which of these things is really the acid here? H plus. So if I give you 2 molar hydrochloric acid, that means I get out of that 2 molar H plus. So what have I really told you that's important? What's really important to calculate pH? I've told you the hydronium or the molarity, right, of the hydronium or the H plus, and you can find pH from that. So calculate right now. What is the pH of hydronium of 2 molar? So you're putting in your calculator what? Negative log, I hear you. 2? What is it? Negative 0.301 or something like that, right? Are you scared of the negatives? No, don't be scared of negatives. It's a superacid. It's pretty strong for HCl. Okay? Yeah.
How do I know which one to use?
You have usually one piece of information given. Anybody else? If I give you hydronium, which formula is the only formula you can use? If I give you hydronium, I can only use that. I don't have any information for that. Nope. I'm finding hydronium there with antilog. I'll tell you how to do that in a second. I don't have hydroxide and hydronium.
Can we do
Yeah,
the
so-
pH equals minus log?
Yeah, that's the only one we could use, right? That's why we use that one. That's how you know which one to use. Antilog. Do you guys have antilog about down your calculator? I don't, so I don't ever use antilog. I use the opposite of log. Well, what's the base of log? 10. So what's the opposite of log? 10 to the negative blank, okay? So antilog is 10 carat negative pH, or 10 carat negative POH. That's the same as antilog, so we'll use some of that, okay? Oh, I forgot about bases. It's all about that base today. We gotta finish this. Okay, so bases are going to make you guys talking about how funny I am? Yeah. I hear you. I know. I try hard. Okay, bases are making hydroxides. The only thing that's weird about bases, and this is the only time you'll do this, you will not do this on acids, is you will have to consider the subscript. So which of our bases had a 2 subscript? Our strong bases. We're talking bases here. Calcium hydroxide. How about barium hydroxide? I'm going to go with that one. Just because that's not on my board. Okay. Calcium hydroxide, barium hydroxide, and strontium hydroxide. If I give you a specific molarity, and I tell you it's one of those subscripts of 2s, I don't want to say dibasic, that's kind of what it's called, then it makes double the hydroxides, because it makes 2 hydroxides when it goes into solution. So if I started you off with 4 molar barium hydroxide, I double the concentration because the basic portion of it is doubled, so I have now 8 molar hydroxide. And this is the part I'm using in the POH formula. Not that part. This part's not really the base. This is the base. So what's the POH of that? Like crazy high, okay? It's good. POH is what? Negative log of 8 molar and negative 0.9. Okay? If the POH is negative 0.9, what is the pH? Which formula are you using? Huh? It's a negative 0.9.
Oh, 14.9.
14.9. And so how are you doing that? What formula are you implementing?
It's 14 equals pH.
Okay, so pH plus POH is 14, and you know the POH to be negative 9, or negative 0.9, sorry. pH plus a negative 0.9 is equal to 14. You're adding 0.9 on that side, so the pH is 14.9. Is that basic or acidic? Basic. And is this thing basic?
Yeah.
Yeah, so it logically makes sense as well. It's really basic. It's over basic. It's super basic. Okay, So let's do some actual practice. We'll do probably 2 or 3 from here, and then I'll let you guys practice yours, okay? Let's do finding pH, pOH, OH concentration, and hydronium concentration. We got to use as many formulas as we can so you guys get practice with them. I'm giving you what? What's the given here? Spell it out for me. I know it says hydroxide. Which one's hydroxide? OH. So I'm telling you concentration of OH is 6.4 times 10 to the negative 5th molar. I'm telling you that. Which of the other questions, which one do you want to go for first? pH? That one's going to take us 2 steps, Jack. Let's go 1 stepper.
Oh, no, wait.
Let's go pOH, because I give you OH. Let's find pOH, okay? You should do all of these examples with me so you have something to look to whenever you do your stuff today. pOH is formula, equation, what do you want to call it? The equation. Thank you, negative log of OH, concentration, okay? Gosh, my board is so off. Okay, so negative log of, guess what, 6.4 times 10 to the negative 5th. I just gave my calculator away. Is it like 4.6? 4.3? Somebody? 4.1? 19? Okay. Alright, so pOH is 4.09. 19. Yeah, 4.19. You probably want to like label your answers because once you get a lot of work on your paper, it's sometimes hard to go back and like, was that the pOH or pOH, right? So pOH is 4.19. What's the next easiest one to get to of all of our things we have to calculate? pH. How do you get pH from pOH? I'm interpreting your gibberish right now. They're saying pH is plus pOH is 14. So subtract. You're subtracting pOH from both sides. So 14 minus 4.19 is 9.81. This amount of work is fine, okay? For you, I know you can do a lot of this in your calculator, but do I have your calculator? No. Okay, I cannot read your minds. Please put a little work on your paper. You writing out the concentration, step 1, that's 1 point. You writing out the pH formula and then inputting your data to solve, circling it somehow, that's probably 2 points for like simply having the correct equation and then implementing the right piece into the equation. Writing out the equation, inputting data, getting new information, another 2 points, okay? You know me, I'm all about showing that work. And last piece we need is what? Hydronium. Can we find hydronium from this? How? You mean the other way? Say again? If I have pH sub, I can't say pH equals. I have to use pH. You see what I'm saying? What other formula has hydronium and pH in it, but I'm using the pH?
Divide by negative log.
No, I can't divide by negative log because it's a logs are not, they'll just multiply. You know what I'm saying? Antilog, thank you. So hydronium is equal to 10 to the negative pH. That formula? Yeah? You with me? I have pH. I can implement it here to find hydronium.
It's not essentially divided by negative log.
It's antilog. I don't know what the antilog function is on the calculator or if it's a button, but it's 10 to the negative. That is the inverse of log.
Yeah.
But it's not the same as negative log. It's not the same thing as dividing by negative log. What? Do this. 10 to the negative pH. So hydronium is 10 to the negative 9.81. So it's like what something times 10 to the negative 10. Thank you, Deuce. What's up? 1 point.
Yeah, 1.5
Times
10.
negative 10. Thanks, drop it. Okay, so this is hydronium, and we're done with that one. But I tried to use as many formulas as I could on that for you guys. Can I go to the next one? I want to do number 5 next. Number 5, yours says magnesium. Lies. It should be calcium. Scratch number 5's magnesium. It should be calcium. I want to do this one, I'm deliberately choosing this one because I want you guys to help me here. So I'm asking for pH, but I want to know pH, POH, hydronium, concentration, and hydroxide concentration. I want to know them all, okay? So what am I giving you?
Oh, no, you can,
Molarity of what? Calcium hydroxide. Okay, so I'm not giving you straight up one or the other. I'm giving you calcium hydroxide, which is what formula? Now, what does this give you?
Hydronium.
How?
Because
Lies. Stop for hydronium. What's hydronium? Hydroxide. Why? How does this give me hydroxide? Okay, because it's a strong base. Okay, strong bases make 100% products. Strong bases make 100% products, meaning calcium, 2+ and 2 hydroxides. Okay, so doubling the hydroxides does what to concentration? Doubles the concentration of hydroxide, right? So I kind of see that up front. I'm like, oh, okay, so really my hydroxide concentration is not that, but what?
102
Double it, don't square it. 0.01. Now we got all kinds of mathematical functions up in here. Okay, so there's our true concentration of hydroxide. Now, what do you want to find? That's too hard. POH. POH is formula of hydroxide, okay? So that should be 2. Somebody plug that in. 2. Okay. You're gonna know the trick. When it's base, when you can make it base 10. So like this right here, write that in scientific notation for me. Negative log of this in scientific notation. 10 to the negative 2. If it's base 10, log is base 10, right? You know how you can go like log base 10, the exponent is the answer? I forget how to mathematically explain it, but it's like log base 10 something and that's the answer. That's 2. That's how you know that. Only if it's 1 times something base 10. So that's just a trick. If you want to use it, don't worry about it. You don't have to calculate in your head. You got a calculator. Next, this is POH, right? What's pH then? What's pH? So pH plus POH is 14. So automatically tell me pH is what? 12. You do not have to show me. Just so that I can totes do 14 minus 2 is equal to 12. You don't have to show me that. If you write the formula and I see your answer, I can see how you got 14. 14 minus 2 is 12. Yeah.
Why did we do the 0.01 out of 0.05?
Because this happens to be the strong base that had a dibasic subscript, 2. So any strong base with a 2 means that as it dissociates, it makes twice as many hydroxides, and the hydroxide part is really the part that's important. So I told you the molarity of that was 0.05. Doubling the hydroxide, or doubling the concentration for the hydroxide gives you that. Okay, what's the next thing you want to find? Okay, how do you want to find hydronium? Oh, I want to do a different one. We haven't done this other formula yet. What's the only formula we've not used? What kind of new stuff? Okay, is equal to the negative 14. Okay, no calculators on this one. See if you can do this. What are you going to solve for here? Hydronium. So you're dividing by hydroxide. So you're dividing by hydroxide here. Okay, that cancels. You're dividing by hydroxide here, but we know hydroxide, right? What is it? Give it to me in scientific notation. Hydroxide's concentration. Okay. How do you mess with exponents when you're dividing? So a negative 14 minus a minus 2.
Oh, you're negative 12.
Negative 12. Hydronium is 1 times 10 to the negative 12 molar, because concentrations are molar, right? 1 times 10 to the negative 12 molar. So you can actually kind of do some of these in your head. And then be proud of yourself, because nobody else can do logs in their head like you guys. It might be from students, but you know, they have to. Okay. We have 8 minutes left. You guys, I already adjusted my first year reading, get through everything. Don't worry about starting problems at 19A or the indicator video tonight. It's like a little simulation. Get through the rest of the pH problems. So right now, you can get through lecture problems 2, 3, 4, and 6. We did 1 and 5, right? And there's 2 practice problems underneath that says homework. You see those on your paper? Yeah? Okay, you got to do all those pH ones, okay? Basically, you will be a master of the pH tomorrow when you come in. And then, let me see your reading guide if you have it. Not right now. I'll open it under the day. You can work on some right now. You have 5 minutes. You can probably get at least 1 question done.